Okay, Chemistry 3111, we had finished the Chapter 18 content. We had finished all of Chapter 18, which is electrophilic aromatic substitution. Then after that, we study SNAR. And then after that, we cover elimination addition chemistry. So we covered all of those concepts. And now we're going to take some time to go over some practice problems. So the first one, and again, these are published to Canvas. The first one is predict the major product for the following reaction. And we're starting it with this secondary alkyl halide, and then we have benzene, and we have aluminum chloride as our Lewis acid. And so this is going to be a Friedel-Crafts alkylation reaction. But just in terms of the mechanism of this reaction, right? The first thing that's going to happen is that your chlorine is going to react with your Lewis acid, your aluminum chloride, right? So it's going to dump its electrons in here. And then we end up with a complex that's going to look like this. So let me just redraw the 5-membered ring. Okay. And then we have Al. I'll just put, well, maybe I'll draw all the bonds. Or no, I'll condense it like this. There we go. So I'll put negative here, positive. Did I miss a bond or miss a carbon? Mr. Dion, what are you doing? All right, sorry about that. Let me fix that structure. There we go. I guess I ruined the whole thing, so I'll just fix it now. So we have something that looks like that. There we go. That seems a lot more reasonable. So I'll erase all this. So we can think about this as a carbocation, right? Because this is going to break apart. So this will break apart. And we'll end up with a secondary carbocation, which is going to look something like this. Okay, and we know that there's a proton here, and that's going to undergo a hydride shift to give us a more stable tertiary carbocation, which is going to look like this. Okay, something like this. And then we know our nucleophile, our aromatic ring, is going to attack that electrophile. So it's going to, I could use a different color. Anyhow, so it's going to attack something like this. And then after you form the sigma complex, it's going to do a deprotonation to restore aromaticity. So I'll just skip all those parts, and we'll just draw the final product, which is going to look like this. Draw a 5-membered ring, looks like this. So there you go. So that's going to be our final product. I didn't ask you to go through all these steps to show it. I'm just trying to provide you with a rationale as to why you get the rearrangement occurring in this case. And again, it's because you go from a secondary carbocation to a tertiary carbocation. All right, so that covers that one. There's our final product right here. So let's move on to number 2. It says provide the structures of the intermediate products and the final product for the following reaction sequence. So we're starting it with benzene, and we're treating that with methyl chloride and aluminum chloride. So that's just a Friedel-Crafts alkylation, and that will make toluene. So toluene or methylbenzene. Then the next thing we're going to do is we're going to hit that with chlorine and heat. Okay, it's chlorine and heat. And keep in mind, that's the same thing as using chlorine and light. And so that's going to give you a benzylic chlorination. And this is a reaction that we would have covered in chapter 17 in some detail. And so that would give you benzyl chloride. So we're only going to chlorinate once. And then in the next step, we're going to treat that with benzene and aluminum chloride. So this is going to be our alkyl halide this time. And so this would be A, this would be B. And so after our next Friedel-Crafts alkylation, so with benzene and aluminum chloride, we're going to end up with this compound. So I'm just going to put phenyl or pH to represent phenyl. So we're going to end up with this compound here. All right, there we go. All right, next one, predict the major product. I'm not going to draw all the rearrangement this time, right? Because you guys are fully aware of if you had, a primary carbocation like this, right? That's clearly going to undergo a hydride shift to give you the more stable tertiary carbocation. And so it says predict the major product. of the reaction. So after the first step, after treating benzene with the isobutyl chloride and aluminum chloride, you're going to end up with mostly tert-butyl benzene, this compound here. And again, the tert-butyl comes from here, right? So this is going to be a weak activator, but this is an ortho-para director. And the next step is going to be a Friedel-Crafts alkylation with ethyl chloride. And so after that step, so I'll put my ethyl chloride and aluminum chloride. That's going to give me the para product. So I'm going to have my tert-butyl group here, my ethyl group down here. And then in the next step, I'm going to do a benzylic oxidation to a carboxylic acid. But of course, only the ethyl group has a proton on it. And so the tert-butyl group is not going to be oxidized whatsoever. So we'll put excess KMnO4, sodium hydroxide, and water, followed by aqueous acid. And so that's going to, again, only oxidize the end that has a benzylic proton. So our tert-butyl group is going to remain intact. And then we're going to have our, excuse me, our carboxylic acid portion down here. So that would be para tert-butyl carboxylic acid, or benzoic acid rather. All right, let's try the next one. Again, these questions really are interested in these rearrangements. So for this alkyl halide, I don't know why it's coming out like that. But anyhow, if we think about this alkyl halide, after it loses the chlorine, after it binds to the Lewis acid, right, you would end up with something that looks like this, okay? Something that looks like that, but we know that oh, I have an extra carbon in there, Mr. Dion. There we go. We have something that looks like this, but we know that is not going to be nearly as stable as the resonance form. So if we draw the resonance form, so if we an allylic carbocation, so we draw the resonance form, which is going to look like this, and that is the part that's going to react because it's more stable, right? The first one was primary allylic, and this one is going to be tertiary allylic, and that's why this is the active carbocation that's going to react in our Friedel-Crafts alkylation. And so in that case, if we had to draw a mechanism for this, what I would do is something like this. So I'd start out with my halide like this, and my aluminum chloride. And I would start by having my Lewis base react with my Lewis acid. So that's going to give me this complex, where I have my chlorine with a positive charge, my aluminum with a negative charge. There we go. And so then, like I said, this is going to leave. So we're going to break this bond, and we're going to end up with this allylic carbocation, but of course that has a resonance form. It's going to look like this. We'll draw the resonance form. There we go. And that's even more stable because it's tertiary allylic. And so that's the part that's going to react with the aromatic ring. So I don't have enough room to put the whole dang thing on here. But if I put the aromatic ring like this, and I say, okay, well, it's going to act as a nucleophile here, I'm going to end up with the sigma complex. And after restoration of aromaticity, I'm going to end up with something that looks like this. So I'll just put missing a few steps here, and then I'm going to have my benzene ring. I have my two methyl groups here. There we go. And of course, I'm going to end up with aluminum chloride, my catalyst being regenerated, and some HCl as well along the way. All right. So there we go. So that's that one. Let's see here. Actually, I didn't even realize I had all this space. I might go back and redo this one when I post it to Canvas so I can put in the sigma complex. All right. The next one, provide the major products formed in each step of the following reaction sequence. So the first one is a Friedel-Crafts acylation. So Friedel-Crafts acylation. And the second one is the Clemmensen reduction with the zinc mercury amalgam reduction. So I think students could put this together very quickly. So if I draw my aromatic ring, so I'm going to treat this with 1, 2, 3, 4. So 1, 2, 3, 4. There we go. So here's my acid chloride. Here's my Lewis acid. And I'm going to end up with this compound. So 1, 2, 3, 4. Then I do the Clemmensen reduction, which uses the zinc mercury amalgam and HCl, and you heat that up, and that reduces the carbonyl. And so I just end up with butylbenzene in this one. So just butylbenzene is going to be my final product. All right. So the ketone is going to be A, and this will be B, like that. All right, next one's a little faster. Which of the following substituents will not direct the incoming group to the ortho-para position? So the first one is just an alkyl group. That's going to direct to the ortho-para position. The next one is a tri-halomethyl group, so trifluoromethyl. That's going to direct to the meta group, so that better be not direct. Yeah, so this better be the answer. The next one is a methoxy. I told you it's the weakest of the strong activators, or the strongest, no, the weakest of the strong activators, or the strongest of the moderate activators. So this is ortho-para. This one is ortho-para, and this one also bromine. It's a weak deactivator, but it is a ortho-para director. That's the exception that we talked about, was the halogen. So the answer for that one is B. The next one, which of the following substituents will direct to the ortho-para position? So let's see here. The first one is an alkyl group, so that's going to direct to ortho-para. The next one is the trifluoromethyl. That's going to direct to meta. The next one is an alkoxy group. That's going to be ortho-para. And then we have a carboxyl group, which is actually, sorry, it's an ester. That's going to direct to the meta position. And so the answer is going to be both A and C. So the alkoxy group and the alkyl group. Number 8, which one of the following substituents will direct an incoming group to the meta position? So meta, we look for deactivators. So nitro is definitely a deactivator. Nitrile is a moderate deactivator. And so that's going to direct to the meta position, as will the trihalomethyl group. So trichloromethyl will, as will the carboxyl. So I guess the answer to this one is everything directs to the meta position. So again, this is meta. Number 9, which of the following substituents will not direct to the meta position? So we already went over most of these. This will direct to meta. The nitrile directs to meta. The alkoxy group will direct to ortho-para, and the carboxyl group will direct to meta. And so the answer is going to be C. Is the only one. Where's my blue pen? It's the only one that won't direct to the meta position. So the answer to that one is C. All right, the next one, it says give the preferred products for the nitration of bromobenzene. So let's take a look at bromobenzene. If I draw bromobenzene, which is just this compound, so you take benzene and you put a bromo on it. There you go. Now if I nitrate this with nitric acid and sulfuric acid, it's going to affect the nitration, but where is the nitro group going to go? Could anybody tell me? Would it go in the ortho, meta, or para position? And it's not a trick or me trying to get you or something like that. I wouldn't do that. So with bromine, remember that bromine is a weak deactivator, okay, but it's the exception, right? Bromo will go to the ortho and para. It's going to mostly go to the para, but it does say products. So what would the preferred products be? Preferred products would be the para nitrobenzene and then the ortho nitrobenzene. So we'll scribble both of them down here. Bromine, and we'll do ortho. So para and ortho. Those will be the two main products. The next one is predict the major product for the following reaction. So we've got some fuming sulfuric acid. And this guy, if you remember, this is called anisole. And anisole has a methoxy group, and that is an ortho-para director. But of course, the methoxy group has free rotation around here. And so we're going to get most of our substitution in the para position. And we're going to put a sulfonic acid in there. So this one's a pretty quick one. we put our alkoxy group like this, and then we put our sulfonic acid, SO3H. On you. There we go, like that. All right, next one, we have an an ester, but you have a carbonyl directly attached to the ring, so that's a moderate deactivator, and that's going to be a meta director. And then you have anisole, so this is going to be a moderate activator, and so it's going to direct to the ortho para. So remember, whichever one is the stronger activator is going to be the directing group. And so the alkoxy group is going to direct to the para position, which already has a substituent, so it's going to block mostly to the ortho substituents. And we're adding a tert-butyl group on there. So all we have to do is put the tert-butyl ortho to the alkoxy group and meta to the to the ester. So we'll start by putting the ester down here. So it's a methyl ester, then we have OCH3 here, and then we have our tert-butyl group. Something like that. All right, give me a thumbs up if you're with me on that one. So we always go with the stronger activator. So if you have something that's moderate, it beats out anything that's deactivating at all. All right, next one is kind of a cool problem because you have a tert-butyl group, which is an ortho para director, but it's going to direct to the para position because it's so sterically hindered. So if we want to put a bromine ortho to it, we're going to have to use a blocking group, won't we? So what we do for our blocking group is we put fuming sulfuric acid, and that will put a sulfonic acid in the para position, essentially blocking it. So we'll put here fuming H2SO4. And so we end up with something that looks like this. And then we have the sulfonic acid like that. Now we can put our bromine in. So I'm just going to put here bromine, Br2 and FeBr3. So we need our iron 3 bromide. And so in that case, we end up with, here's my tert-butyl group. Here's my sulfonic acid. And here's my bromine. Does anybody remember how to remove the sulfonic acid? Does anybody remember how to get rid of that blocking group? Yeah, thanks. Thanks, Erica. Dilute H2SO4. Rock and roll, organic chemistry. Let's keep going. Okay, the next one is provide the reagents necessary to carry out this transformation. Now keep in mind you have a positive charge on the nitrogen here. That deactivates the ring so strongly it's hard to believe. I mean, so this is going to be a meta director, whereas the oxygen from your alkoxy group, that's going to be an ortho para director. Now nothing's going to be directed in between the two, so nothing's going to be directed at this position. But then between the two of these, you have the methoxy, which is a moderate activator, and then you have the trimethylammonium portion over here, which is going to be a strong deactivator. And so who wins? Well, the person or the group that wins is going to be the activator. And so we don't need any blocking group or anything like that. So all we would need for this case to install the ethyl group is just ethyl chloride. And we'll use aluminum chloride as our Lewis acid, and that's it. The next one, number 15 and 16. So there's two problems here, obviously, but these are good to just kind of help remind you, the order of operations is very important in these reactions. So the number 15, we have a nitro group, which is a meta director, and then we have the bromine, which is an ortho para director. And so which one should we put in first? Well, we'd have to put the nitro in first because that's going to direct the bromine to the para position. If I did the bromine first, it would direct the nitro to the para position. So let's just write down our reactants. So for the first part, to nitrate it, we're going to use nitric acid and sulfuric acid together. That's going to install the nitro group, which is going to install the bromine in the meta position. So for the bromine, we just need bromine and iron 3 bromide like that. The next one It's kind of like flipped around because now you have the halogen and the nitro group para to each other. Again, they're meta in this one, but now they're going to be para. And so we have the nitro, which is a good meta director. We have the chlorine, which is an ortho para director. And so the chlorine should go in first. So in the first step, we'll take chlorine and aluminum chloride, like that. And that puts the chlorine in. And in the second step, we're going to install the nitro group with nitric acid and sulfuric acid. There we go. Give me a thumbs up if you're with me on 15 and 16, just how the order of operations works. Okay, cool. Awesome. Good. Just wanted to be sure. The next one, I like these where it's just benzene and then you get some product. Okay, so this one's kind of in the same vein as number 15, I guess, because you have the acyl group here, which is a meta director. Then you have bromine, which is orthopara. So obviously we have to put the acyl group in first because it will direct the bromine to the correct position. So to install that acyl group, in step 1, we're going to use the acid chloride and aluminum chloride. And that would install the acyl group. And then in the second step, we're just going to use bromine and iron 3 bromide, like that. Okay, next one. Again, a little more involved, number 18. Why? Because you have two groups that are ortho to each other. So we have the ethyl group, and then we have the bromine, and they are ortho to each other. So how are we going to get the bromine ortho to the ethyl group? Well, I think the best thing to do would be to put the ethyl group in first, then put a blocking group in, right? If I could just put the blocking group in, let's say I had this compound. Let's say I had my ethyl here, but then I had the blocking group here. If I treat that with bromine and iron tribromide, that's going to put the bromine in the correct position. So I need to put the ethyl group in first because it's para-directing, and the sulfonic acid is not. It's actually a meta-director. So we'll put the ethyl group in first, then we'll put the sulfonic acid, then we'll put the bromine, and then we'll remove the sulfonic acid. So what does that look like? In step 1, we're going to use ethyl chloride and aluminum chloride. In step 2, we're going to use fuming H2SO4, and that is going to install the sulfonic acid. Then we can put in the bromine. So for step 3, we're going to use Br2 and FeBr3. So that would put everything where we need it, but now we need to remove the sulfonic acid. So we'll put dilute H2SO4, like that. And that takes care of the whole kit and caboodle. All right, next one. I think the next one actually deserves a little bit of a retrosynthetic analysis because we have a carboxylic acid, and I haven't taught you many ways to make a carboxylic acid, really. But if we had this compound, what if we had parachlorotoluene, right? Remember, we could do an oxidation with chromic acid, and that would oxidize the methyl group all the way to a carboxylic acid, right? They both have one carbon. So now the question becomes, well, how do I get from here to here? Well, you have the methyl group, which is a weak activator, and then you have the chlorine, which is a weak deactivator. So I would put the methyl group in first, and then the chlorine in second, because it's going to give you a higher yield. And so in step 1, we're going to use methyl chloride, chlorine, that installs our methyl group. Then in the second step, we're going to use chlorine and aluminum chloride. So that's going to make the compound in blue. Compound in blue would be done. Then in the last step, you just need to oxidize the methyl group to a carboxylic acid. So for that, you need chromic acid. I'm going to use sodium dichromate, sulfuric acid, H2SO4, and water, like that. All right, there we go. So that's a 3-step synthesis, upping the ante here. The next one, number 20, you have an isopropyl group on one side. So here we have isopropyl. propyl, and then here we have just a plain old propyl. Well, we know we can't put a propyl on using a Friedel-Crafts alkylation because we'll get a mixture of the propyl and isopropyl. So I think it'd be wise to put the isopropyl in first, then put in the propyl group as part of an acyl group, and then just reduce this compound. So make this and then reduce it using a Clemmensen reduction. Would probably be the best way to tackle that. So what's that going to look like? There we go. So what that's going to look like is this. This time I'll actually write out the whole thing. So the first step is going to be isopropyl chloride and aluminum chloride. Let me erase that. And that's going to give you the paramethyl or the isopropyl compound. Then we need to do the Friedel-Crafts acylation. So for that we need how many carbons? 1, 2, 3. So 1, 2, 3, and aluminum chloride, and that's going to give you the acyl compound. Running out of space here, but you get the idea. All right, and then after that, to get to the final product, we just do the Clemmensen reduction. So we use the zinc mercury amalgam with HCl and heat. I like that. So what I'd like to do now is take a short break, and I'd like you to try 21 is a little bit tricky. Let me give you a tip about 21 because I looked over these very carefully before class today. With number 21, your actual precursor to the final compound is going to be this. So you're going to have the secondary alkyl halide there, and then you're going to need to do an SN2 on it. So that's the kind of retrosynthesis of that one. 22 is relatively straightforward, as is 23, 24, 25. You can do that without my help. That looks good. Oops, didn't mean to do that. I think that one that is also challenging is 27. So I'll show you kind of my strategy is to get to something that looks like this. So you can use a Friedel-Crafts acylation, and then you can just use Greenyard, right? You could use methyl magnesium bromide, and it's just going to keep adding if you add it in excess to make the methyl alcohol here, or the tertiary alcohol. This one is also in the same vein as another one, as is this one. And then we have these guys here, which are not straightforward, but definitely doable. So those are my hints. So what I'd like to do is take a few minutes, and I'd like you to try the rest of these and see if you can come up with a couple of syntheses here for these compounds.